All right, now for the next definition. And it's hard to overstate the importance of these notions here. The definitions seem trivial, but it takes some time to get used to them. So pay close attention. As always, F is a map between sets A and B. F is called injective if f of x equals f of x prime implies that x is x prime. Or the contraposition of this fact, if I negate this, then the negation of this must follow, meaning if x is not equal to x prime, then the images of both cannot be equal. This means injective. And here, maybe more easy to grasp in words, no element of the codomain gets hit more than once by the map F. So it's not possible that two different elements get mapped to the same y here. If this happens, then the map is not injective. So now the next notion, F is called surjective, or sometimes onto. I do not like this term so much. I'm going to prefer surjective if for all elements in the codomain there is an element in the domain such that f of x is y. And this means exactly that the image of f, so f of the set A, is all of the codomain B. Here again, using words or more words, every element in the codomain gets hit at least once by the map. I don't know if this hit is too harsh a word, but it's not in a martial sense, but simply f hits an element when it maps element of A. So here, no element gets hit twice or more than twice, and this means every element gets hit at least once by the map. And both taken together, so injective and surjective, is called bijective or one-to-one correspondence. And this means these taken together that every element in the codomain gets hit by F exactly one time. And then I have a one-to-one correspondence between the set A and the set B. All three of them are fundamental notions when dealing with homomorphisms, so you really have to try to understand these completely. Okay, let's take a look at an example. So to understand these new concepts, let's first take a look at our nice everyday example here with the favorite snacks of those persons here. The yellow map F, is it injective? No. Why? Because cookies here gets hit twice by F. Both Barbara and Charlie like cookies best, so this contradicts injectivity. There is more than one pre-image of this element here, so this map is not injective. Is it surjective? Well, no, because those here, bananas and donuts, are not hit at all. So the image of F is not the complete codomain, and this means that this map here is not surjective. So this is an example for a neither injective nor surjective map. What about F tilde? Well, it's no map at all, so we do not have to talk about injectivity or surjectivity. Okay, how about G? Well, G is clearly surjective because both elements in the codomain are hit by G, or simply here because G of A, the image of G, is the whole codomain. So this is a surjective map. Is it injective? Clearly not, because here C has two different pre-images. Y and Z both get mapped to cookies. So this contradicts the definition of injectivity. Or in other words, this here is hit by more than one element. So not injective, but surjective. Now in the last example, this clearly is a bijective map. It is surjective because its image is the whole codomain. Every element here gets hit, and every element gets hit only once. Yeah? All the pre-images are unique, so this means injective. Or in other words, no element here gets hit more than once by H. So this is injective and surjective, meaning bijective. And you clearly see the one-to-one correspondence between both sets under this map H. And now it's not so hard, it's actually on the next problem set to see that if I have this situation, if I have finite sets such that the domain has more elements than the codomain, it's impossible to find an injective map. Surjective, sure, but injective, not possible. And for a map to be bijective between two finite sets, they both have to contain the same number of elements. All right, next example. It's also pretty trivial, but we'll leave it at that, and there will be a lot more examples in the exercises. And again, I strongly encourage you to do most of them. So we take a look at the so-called right shift, lowercase rho, lowercase r in Greek alphabet, rho, from the natural numbers to the natural numbers, listed here. Remember, 0 does not belong to the natural numbers in my notation here. What does rho do? It simply shifts a number to its successor. N is mapped to n plus 1. So 1 goes to 2, 2 goes to 3, and so on. Now, if you already understand the concept of injective, it should be clear that this map is injective because no number gets hit twice by rho, but let's prove it. So let's assume rho of n is the same as rho of n prime. This means actually, this implication would be enough, but clearly this is an equivalence. And subtracting 1 on both sides yields n is equal to n prime, so this is exactly the definition of injective. Or if n is not equal to n prime, then of course if I add 1, they won't become equal. So this map clearly is injective. Is it surjective? Well, for this map to be surjective, its image would have to be all of the natural numbers, but clearly here 1 is not hit. 1 has no pre-image. Because we have no 0 here that we could map to 1. So 1 is not in the image of rho, therefore rho is not surjective. All right, and one last time, please do the exercises. Okay, now the next notion we already know. We have worked with composition a lot. Now here's the general situation. If F is a map from A to B and G a map from B to C, then I can build their composite or composition. At least in German we say that. Maybe it's not correct in English, but forgive me if I also use composition instead of composite. G composed with F, and this is a map from A to C, defined as follows. G composed with F applied to an element A is simply G applied to F of A. So in this picture, if this is an element, then this here is mapped to F of A, and then this gets mapped to G of F of A. And of course, this is just a suggestive picture. The sets do not have to shrink under the maps or whatever. So, and the composition then is this map here that moves A directly to G applied to F of A. This is the composition G composed with F. In German we say G after F. I'm not sure if this is used in English as well. And when you think about the symmetries, the permutations and so on, we already used that a lot, so this should be clear. Okay, and now finally, to conclude our digression into the theory of maps, a very important proposition 15 that uses the notion of composition of maps in relation to the terms injective, surjective and bijective. So, as always, let F be a map between sets A and B. If there is a map from B to A, so in the other direction, that we call G, do not confuse it with this picture here. We only have two sets now. F goes from A to B, G goes back from B to A, such that the composite of G with F is the identity of which set? Well, of A, because remember we read from right to left. So we start with F, going from A to B, and then applying G, we go back from B to A. So if it is the identity, the identical map, it must be the identity of the set A. And this simply means the map that does nothing, that if I plug in a lowercase a, I end up with the same A. If this is true, that there is such a map that this here holds, then F is injective. The other way around, if there's a map, again from B to A, this time I call it H, such that the composite of F with H, now H is first, so we start in B, go to A, and with F we go back to B, is the identity of B, so the identical map that does nothing to the elements of B, then F is surjective. And both taken together, of course, then F is bijective, if and only if there's a map. Now G and H are the same from B to A, such that both conditions are fulfilled at the same time. And this G here is uniquely determined by F, and now it is denoted by F inverse. As I said many times before, F inverse has two meanings. First of all, it can mean the pullback, the pre-image under any map. But here, if the map is bijective, it actually is again a map, now from B to A, and it is denoted also by F inverse. So I hope that is not too confusing. All right, if this is new to you, then doing this proof on your own might actually be much too hard. If you have already heard this before, this would be a good time to pause the video and try to prove this. If you can do that without problems, then you are pretty well acquainted with the notion of map composite and bijectiveness and so on. Okay, now let's tackle the proof together. If you could do it on your own, please leave a comment. I will be happy for you and congratulate you. Let me warn you that the proof here is deceivingly simple. If you see this, you think, oh well, I could have come up with that. But could you have? I don't know. So we have to show injectivity. We use the definition. So we assume that the images of two elements x and x prime are the same. We have to conclude that then x already is the same as x prime. Now here we use the fact that of course we have to use this map G. G is a map, meaning if I plug in this or this, it can make no difference because these are the same elements of B. So if I apply a map to it, I must end up with the same element. But this is already important that you understand this step here. So if you write this down as a solution to an exercise, please write down here in the corner that this uses that G is a map, hence images are unique. So from this follows that, but now here we have nothing but the composite G composed with F. But this is the identity. So here, this is nothing but the identity of A applied to X, because this by definition is G composed with F applied to X. And here the same. This is the identity of A applied to X prime. So this already means that x equals x prime, and we have shown that f is injective. That's it. Okay, and it's always a good idea to write down what you actually have to do if you're not sure how to do it. So, number 2, we have to show that f is surjective if such a map H exists. So surjectivity means if I take an arbitrary element of B, then there must be a pre-image, meaning an x in A, such that x gets mapped to y under F. So, of course, we have to use this map H that goes from B to A. So what else can we do but plug in y into H? So we move y back to A using H and define x as H of y. Then, so this is a definition, so here should be this colon, x is defined as H of y. Then what is f of x? F of x is f of H of y. Now this time let me spell it out. I was too restrained here because I want to fit this proof on the rest of this blackboard, I'm sorry. So this is what I should have done here as well. This is nothing but the definition of the composite. F composed with H applied to y is simply that, but now F composed to H is the identity of B applied to y, but the identity does nothing to y, so we end up with y, and that is it. That's exactly what we needed to show. So we have found out F is surjective. Also deceivingly simple. Now, statement 3, here's an if with two f, so we have to show both directions. Let's do the easy one first. Let's suppose there are maps that satisfy this here. Then it is clear by 1 and 2 that f is bijective. Why? Because this here means f is injective. This here means that f is surjective, so both taken together simply mean that f is bijective. So this is clear. Now the other direction is harder. Let f be bijective, then we need to find such a map. Okay, now the idea is easily obtained by using such a diagram. And this in this case I think is okay. We have a one-to-one correspondence between elements of the set A and elements of the set B. So all we need to do, here in yellow we have the map F. So all we need to do to find this map G is reverse the arrows. And we have to find out if this is actually a map from B to A. If I call this here y, then I know this is of the form f of x for exactly one x, which I call x sub y. So if I define G from B to A by mapping y to xy as explained here, I get a map y. Again, every element of B is of this form because f is surjective, right? So every y can be written as some f of some x. And because f is injective, this here is unique. If f were not injective, I might have a problem because then, for example, those two guys could be mapped to the same y, and then I would have to make a choice. So this rule here would not be a map at all, because one element would get mapped to two or more elements. It would only be a relation. But because f is surjective and injective, this here is a well-defined map from B to A. You will forgive me that I'm not trying to put this into writing here in this little space I have left, but if you try to make notes, please definitely do that. Go back 1 or 2 minutes in this video and write that down. Simply as I've explained it, this here defines a map. And now, does this satisfy these relations here? Well, trivially, because let's look at this composite here. G of f of x. I start here, I map this to f of x, but what happens if I apply G? By definition, I end up with the x I started with. I dropped the index y now. Okay, so clearly this here does nothing to an element of A, so this is the identity. This is exactly what I wanted. Now, with reversed order, first G, then f. And this must be applied to an element here. So G of y and then this plugged in into f. What is that? g of y is exactly this xy here. And f of xy by definition is y. So this map here does nothing to an element of B, so this means this here is the identity of B. And this is what was claimed here. Whew. Okay, to be honest, I'm pretty exhausted now. This lesson was by far the hardest I have recorded yet, but it's very necessary to go through all these things, especially for beginners who haven't heard them before. So let me simply tell you that by construction it is of course unique, because I have no choice left here for G if I define it in that way. This is a bit of a cheat, but I hope you can live with that. And from now on, we know that if f is bijective, there is a unique map called f inverse going from B to A, satisfying exactly this here. Okay, this is maybe a B- or C+ for writing down, but I hope I could convey the core ideas of this proof here. And chalk drop and goodbye. All right, I know this is a friendly introductory course, so I cannot just tell you, well, this is clear by construction. So let's try to squeeze it into the last free line here on this blackboard. Of course, not a chance that I can put the idea here in good writing, but you're also supposed to learn to do that on your own. Also, when you're hearing a lecture, the professor will not give you all the sentences and all the details, but he will write down some symbols and you have to make sense of taking notes yourself. So you have to fill in the missing spots. All right, do that here. So we assume there is another map, G tilde, that fulfills the same conditions. Yeah, we have a bijective map. We know there is at least one map G that satisfies this, and now we assume we have another one. This is a pretty standard way to prove uniqueness, but this means there must at least be one element of B such that the images of this element are not the same, because otherwise the maps would be the same. If they map all elements of B to the same, then they're the same maps. Okay? So we find such a Y that this holds, and now we have two different elements. We know that F is bijective, so in particular it is injective. So if we apply F to these different elements, then the images must also be different, because F is injective. But now look what we have. This here is F composed with G applied to Y, but F composed with G is the identity. And this here is F composed with G tilde applied to Y. But this also is the identity, because we assume G tilde is another map that satisfies this here. But then we have Y is not equal to itself. This, of course, is absurd, so this cannot have been true. So by way of contradiction, we proved that actually the inverse map is unique, because otherwise we would arrive at the contradiction that an element is not the same as itself. Whew, okay, now the proof is complete. Not written down perfectly, maybe at most a B- or C+ for the style of writing that down without much words, but I hope you could fill in the details yourself and that you could understand the core ideas. I think this is the most important here in dealing with this stuff. All right, that's it. I'm begging you, please take your time to do problem set number 12. Do as much of the exercises as you can. You are given 2 weeks time if you follow this course regularly, so that all these new notions can sink in and that you have enough time to really work thoroughly through problem set number 12, which would be very important for the rest of this course. And now all the hard work is done, at least for a while, and we will continue to do some fun group stuff working with homomorphisms and isomorphisms in the next weeks. Hope to see you there. Oh, come on. All right. and bye-bye.